Chapter 16 is about solubility and complex ion equilibria. We did this topic in intro chemistry, so the first part of this discussion will be a bit of review, at least this first section of material. Solid equilibria. Remember, there is a value of K, like we had Ka and Kb and Keq. We have something called KSP. What is KSP? It's a solubility product, or equilibrium constant, and it has a value for a solid as it breaks into its ions. Usually we have something like this, element, silver chloride, compound. And silver chloride breaks into ions, but not very well. So we would say that the equilibrium tends to lie towards the left, and the KSP value is a very small number. So solubility product is KSP. Solubility is an equilibrium position. In other words, how much was able to be dissolved. Solubility depends on different factors, things like, of course, temperature, and it depends on how many ions are in the solution. So here's an example of bismuth sulfide. You notice Bi2S3 solid breaks apart into its two ions, and now we remember to balance the equation. When we had acid and base, of course, only one hydrogen was released at a time, and therefore we didn't have to worry about balancing equations. With this information, KSP, we do have to remember to balance. And the KSP is bismuth ion squared times sulfide ion to the third power. Notice that bismuth sulfide, however, as a solid, is not included, and therefore KSP values do not have denominators. So let's see what we have to know from this particular section. In comparing several salts at a given temperature, does a higher KSP value always mean a higher solubility? Well, in a sense, you'll see it says explain if yes, explain and verify, if no, provide a counterexample, which we will do. And the answer is actually no, because it depends actually on the number of ions in solution. Sometimes the solubility can be higher depending on how many ions we have in solution. So here is an example. Calculate the solubility of silver chloride in water, and the KSP is 1.6 times 10 to the negative 10. And then we're going to calculate the solubility of silver phosphate in water, and the KSP is 1.8 times 10 to the negative 18. So let's see what the solubility is. Now you can see the KSP values of silver chloride and of silver phosphate very different. Clearly silver phosphate looks like it's not very soluble because the number is 1.8 times 10 to the negative 18. So now we need to calculate the solubility. How do we do that? Well, the first thing we need to do is we need to write an equation for silver chloride solid breaking into its ions, which I've already done on an earlier page, but I'll do it here. I'm going to do the same thing for silver phosphate breaking into its ions. Alright, now essentially what we're trying to do is to figure out what is the solubility of silver chloride. You can see that the concentration of silver ions and chloride ions in silver chloride is a 1:1:1 ratio. Down here, it's a 1:3:1 ratio. So how are we going to solve? Well, we know that the KSP value is the concentration of silver ions times chloride ions, and in the bottom one, the KSP value is the concentration of silver ions cubed times phosphate ions. So what we're going to do is we're going to plug in the KSP value given, And we know the ratio here is 1 to 1. So whatever silver is, so is chloride. So essentially, if you take the square root of 1.6 times 10 to the negative 10, you get 1.3 times 10 to the negative 5 molar. So that's also the concentration of AgCl. That's the maximum concentration it can be and be soluble. Down here, doing the same thing, we see that the ratio is 3 to 1. So this is 3x and x. Notice the 3x is also cubed. You might think, well, you've already taken that into consideration when you put the bracket cubed, but you also have to triple it because the ratio is a 1 to 3. When you work this out, and of course this equals 1.8 times 10 to the negative 18, you will get 27 x to the fourth equals 1.8 times 10 to the negative 18, and x equals 1.6 times 10 to the negative 5 molar. And that's the maximum concentration Ag3PO4 can be to be dissolved. You will notice that that number is actually larger than that of silver chloride. So the answer to the previous question, which says, explain or verify, whatever, you can see that just because the KSP of silver phosphate is very low doesn't mean the solubility is low. It just depends. In this case, this isn't true. Okay, moving ahead. Oh, and there we go. They're giving the answers. Yep, so those are two different numbers. All right. How does the solubility of silver chloride in water compare to that of silver chloride in an acidic solution? In other words, we make it by adding nitric acid to the solution. And you're going to see that the solubilities are the same. But sometimes that's not the case. Now with silver chloride, remember, silver chloride, if we think of this salt as silver hydroxide, I don't know why I wrote the parentheses. There we go. And chlorine, you can see that this is a strong acid. Strong acids do not tend to be more soluble. I mean, salts of strong acids do not tend to be more soluble in acidic solutions. Solubility is affected by pH, and in general, when the negative ion is a good base, in other words, HX is a strong acid, is a weak acid. I was thinking HCl was a strong acid, but if it's a weak acid, then it will be more soluble. In an acid. So, in this case, the answer is no, and you can see that's what it said. Okay, how does the solubility of silver phosphate in water compare to that of silver phosphate in the acidic solution? Silver phosphate is more soluble and acidic, so let's check it out and figure out why. Silver phosphate. So we're really looking at the phosphate part. HPO4 negative is the acid. This is a weak acid, and remember, weak acids are more soluble in acidic solutions. So that's why silver phosphate is more soluble in acidic solutions. Alright, now we want to calculate the solubility of AgCl in 100 milliliters of 4 times 10 to the negative 3 molar calcium chloride. So how would that work? Well, we know that silver chloride, which we had before, AgCl, has the concentration of silver ions and chloride ions to be 1.3 times 10 to the negative -5 molar, which is what I found in an earlier slide. Now, you'll notice that when AgCl breaks apart, I should have not written it that way, in the beginning, you know, silver has virtually, it's such a tiny number, we don't count it. But chloride ions, because calcium chloride, you notice CaCl2, calcium chloride has a common ion in common with silver chloride. So the concentration of chlorine ions is 4 times 10 to the negative 3. Now, calcium chloride, you notice, when it breaks apart, it forms calcium and chloride ions. 2 chloride ions for every calcium chloride. So therefore, if the concentration of calcium chloride is 4 times 10 to the negative 3, then chlorine is 8 times 10 to the negative 3, and calcium is 4 times 10 to the negative 3. So therefore, chlorine ions, when added to silver chloride like this, is 0.008 molar. I'm just writing it because it's a shorter number to write there. I could have written 8 times 10 to the negative 3 as well. So that's initially. And then there's some change. Of course, in this case, we are adding something. We don't know what, and subtracting it from AgCl, but since it's a solid, it doesn't matter. So we have X, and we have 0.008 plus X. And silver chloride, of course, has a KSP of 1.6 times 10 to the negative 10. So 1.6 times 10 to the negative 10 is equal to X times 0.008 plus X. Because the value we're going to get for X is so tiny as compared to, 1.6 times 10 to the negative 10, this number I'm going to cancel to make the solving easier. And when we do, we should get 2 times 10 to the negative 8 molar, and that's what I got. Just what they got. Now, how would the solubility change if we had a different, oops, don't look at that. Well, I guess we will, because we're giving the answer. If we had a different substance, calcium nitrate. Now, we can see that the answer is 1.3 times 10 to the negative 5. So, why would that be the case? Well, again, silver chloride, solid, breaks into silver and chloride ions. We can see that there's virtually no silver in the beginning, and there is no chlorine in the beginning. So therefore, what is the solubility of AgCl? The solubility of AgCl is the same as the silver ions, because in this case, I guess you could say, which we said was what, 1.3 times 10 to the negative 5. That's the biggest number there. 0.008 is significantly bigger than that, so that's why I put 0 in the beginning, because it was such a tiny number. So essentially, the concentration of the silver chloride, or the solubility of silver chloride, is the same as the silver ions, because calcium nitrate essentially has no effect, because it has no common ion.